Welcome to a new topic, force on a dielectric and Clausis-Mossotti equation. In the last session, we have discussed the concept of polarization and electric displacement and some idea about a dielectric system, its susceptibility, energy stored in a dielectric system, etc. Now in this session, we are going to discuss some other properties of a dielectric system and some special cases. As a first case, let us start with a problem. Consider a sphere of radius r which is completely a dielectric material which is placed in a uniform electric field E0. So we have to find out what is the resultant electric field inside the sphere. For that, we will consider a sphere of radius r kept in an external electric field E0. So this is the electric field E0. So if the E is the external electric field given and P is the polarization, then the amount of polarization induced in a dielectric material is given by our old expression P is equal to epsilon 0 chi E into E. Here, for a sphere, this inside the dielectric new electric field is due to the induced polarization. Okay. Now, which is given by the expression the new electric field we had derived in the last class inside is equal to, for a sphere which is equal to minus P into P by 3 epsilon 0. Now, in this problem, the induced polarization is given by P0 is equal to epsilon 0 chi E into E0. Why E0? This E0 is the applied electric field, which induces a new electric field which is given by the expression E1 is equal to, we have to substitute for P0 here, which is equal to epsilon 0 chi E E0 by 3 epsilon 0. This epsilon 0 and this epsilon 0 will go and remaining will be minus chi E E0 by 3 epsilon 0. So we have E1 is equal to minus P0 by 3 epsilon 0. We substitute for P0 and we obtained as minus chi E into E0 by 3. Thus, E1 further polarizes the dielectric sphere, and now the polarization is given by P1 is equal to minus epsilon 0 chi E into E1. So there is no P1 is equal to epsilon 0 chi E into E1. This P1 induces its own electric field which is given by E2 is equal to minus P1 by 3 epsilon 0. So again, what is P1? P1 is equal to epsilon 0 chi E into E1 divided by 3 epsilon 0. And here also epsilon 0 will go, and which will be minus chi E E1 by 3. And from our old expression, E1 is equal to, what was E1? E1 is equal to minus chi E by this epsilon 0 and there is no epsilon 0 here, which is equal to chi E 0 by 3. I am substituting this E1 on this equation, which is equal to E1 or E2 will be minus chi E by 3 into minus chi E E0 by 3, which will obtain as chi E by 3 the whole square into E0. Again, this electric field again induces, which again polarizes the amount P2 and the system, and this process continues. So the effective electric field or the total electric field due to the contribution of n polarization is given by En is equal to minus chi E by 3 whole raised to n E0. And what is the value of n? N runs from 0, 1, 2, etc. up to infinity. Since this expression can be expanded in terms of a geometric series. So, how can I expand in terms of a geometric series? We have E n is equal to minus chi e by 3 whole raised to n E0, and there is a summation here over n is equal to 0 to infinity. So, I can write E n, the total electric field, is equal to E0 plus, so and for n is equal to 1, which is equal to minus chi e by 3 E0 plus chi e by 3 the whole square into E0 plus, like that it will go. So, this is a geometric series, and the first term A is equal to E0 and R is equal to minus chi e by 3. So, their total sum S is given by S is equal to A by 1 minus R. So, substitute that and we will obtain E inside is equal to 3 E0 by k plus 2. And remember, what is this k plus 2? Where it is coming from k is equal to chi e minus 1. Substitute the fact that k is equal to chi e minus 1 and obtain, you will obtain this expression as 3 E0 into divided by k plus 2. So, which shows that electric field inside the dielectric sphere is proportional to the applied electric field, where E0 is the applied electric field. Now, let us find out, if a dielectric medium is placed in an electric field, what is the force it experiences? Consider a slab of linear dielectric material partially inserted between the plates of a parallel plate capacitor. So, I will draw a parallel plate capacitor which has a plate separation as D. The plates are separated by D. Now, I will insert a dielectric material of thickness D in between the plates as shown in the figure. Now, I have just inserted a distance S over this, and the total width of the plate is W and the length is A. So, I have to find out what is the force or what is the work done first. So, I have to find out what is the force acting on the dielectric slab, so that I have to do a work done to pull the slab out of the capacitor plate. Small work to be done to pull the slab through a small distance is given by dW is equal to F external into ds, and this F external is nothing but is opposite of the force exerted by the dielectric. Therefore, it is clear that the capacitance of a capacitor and the potential difference between the capacitor plates are not same for the entire arrangement, but the charges on the capacitor plates are uniformly distributed. So, we can write W is equal to Q square by 2C. So, we have derived this expression for work done, W is equal to Q square by 2C. So, from the figure it is clear that the arrangement is like a parallel plate capacitor. So, what is the force? F is equal to, from this expression, F is equal to minus dW by ds. So, we have to substitute for W. So, F is equal to minus of d by ds of Q square by 2C. Since the charge is constant, which is equal to minus Q square by 2 into d by ds of 1 by C. On differentiation, we will get Q square by 2 C square into dC by ds. So, what is this dc by ds is the next question. Since the slab is partially filled inside this parallel plate capacitor as per the figure, partially filled, this is actually a capacitor filled with air, and this is a capacitor filled with a dielectric connected in parallel. So, we know that the capacitance of an air capacitor is given by C air is equal to epsilon 0 A by D. Epsilon 0 A by D, and we know that what is A, then for an air part which is equal to epsilon 0 A into that small letter A, I have to use small letter A because it is the length, which is equal to A into W minus S divided by D. So, which is equal to, this is the for the air, which is equal to epsilon 0 A W by D minus epsilon 0 A S by D. And for a dielectric, then obviously it is epsilon A by D. And from our last session we got epsilon 0 into K is nothing but epsilon. So, I have to substitute C dielectric is equal to epsilon 0 into K into A by D. And this area is the area of the dielectric substance. So, which is equal to epsilon 0 K into A into S by D. S by D. Therefore, the total capacitance is CT, C total is equal to C of air plus C of dielectric. On substitution, what was C of air? C of air is equal to epsilon 0 A into W minus S by D plus epsilon 0 K into A into S by D. S by D. So, on substitution, you will get C total is equal to, and rearranging what all terms will go. Only remaining term will be epsilon 0 A into W by D plus minus epsilon 0 A S by D plus epsilon 0 K into A into S by D. So, we have to differentiate this, which we want to find out what is dc by ds, and we have to substitute in the equation for F. And for the F, I will use the fact that Q by C is nothing but V. So, Q square by C square is equal to V square. So, you differentiate this equation and we will get F is equal to epsilon 0 A by 2D into V square into K minus 1. K minus 1. And also you can rewrite the expression by using P is equal to epsilon 0 chi E into E, and using the equation E is equal to V into D, the force on a dielectric is obtained as half into P into A into V. So, this is also this is the force acting on a dielectric slab kept in between the parallel plate capacitor. Now, we are going to find a relation between polarizability and susceptibility of a non-polar molecule. When the density of the molecule is very low, the interaction between the molecule can be neglected. But if the dielectric medium has a high density, electric field produced by each tiny dipole is also should be considered. Since the molecules are very close to each other in a high density dielectric medium. Imagine that a sphere of radius r is assigned to each molecular dipole, then the molecular density is given by n is equal to 1 by 4 by 3 pi r cube. So, here a sphere is considered as assigned as the each molecular dipole of radius r, and it is kept, and there is its electric field is due to its electric field due to its polarization, and that's elsewhere the electric field around that. So, E self is the average electric field over the surface due to polarization by itself, while E else is the average electric field due to all molecules outside this sphere. Then the molecular density is given by n is equal to 1 by 4 pi 3 r cube. So, the total electric field E can be written as E is equal to E self, that is electric field self of the sphere, plus E else, and E else is the outside electric field of this sphere. So, we know that the dipole moment is equal to alpha into E else, and the polarization P is given by n into alpha into E else if there are n dipoles. And also we have the expression for an sphere E is equal to E inside, that is E self has the expression minus P by 3 epsilon 0. And what is this P? P is equal to n alpha into E else. So, I have to write E self has equal to minus P by 3 epsilon 0 into E else. So, I have to substitute for this E self in the equation E is equal to E self plus E else. So, I can rewrite E is equal to, what is E? E is equal to minus n alpha E else divided by 3 epsilon 0 plus E else. So, I have to clear this. This is not P. So, I have to take this P and I have to rewrite as n alpha. So, n alpha E else divided by 3 epsilon 0. So, we can obtain from this equation, I can obtain the expression for E else. What is E else? Rearrange and you will find out is E else is equal to E by 1 minus n alpha by 3 epsilon 0. 3 epsilon 0. So, P is equal to, then what is P? You have to substitute for P. So, P is equal to this equation, substitute for E else in this equation. So, P is equal to n alpha into, what is E else? E divided by 1 minus n alpha by 3 epsilon 0. N alpha divided by 3 epsilon 0. And what is P? P we know that in general P is equal to, what is P? Epsilon 0 chi E into E. Chi E into E. So, use these two equations. Use these two equations, you will get a relation between chi E and K. But because we know that chi E is equal to K minus 1. We have already obtained this equation. And we know that epsilon 0 chi E into E is equal to n alpha into E divided by 1 minus, what was that? 1 minus n alpha by 3 epsilon 0, n alpha E, n alpha by 3 epsilon 0. So, you can substitute for chi is equal to K minus 1. So, you will get chi is equal to n alpha into K plus 2 divided by 3 epsilon 0. So, substitute and find out, and this equation is basically the relation between dielectric constant, polarizability and the susceptibility. And again you can obtain the equation for alpha as alpha is equal to, rearrange the term and you will get 3 epsilon 0 into k minus 1 divided by n into k plus 2. You have to obtain these two equations, and these two equations are called the famous Clausis-Mossotti equation. And there is another connection between electric susceptibility and the temperature. As the temperature increases, the electric susceptibility decreases. You can easily find out why this is so. As the molecular alignment is broken because if we are supplying energy to the molecule. So when the molecules get the energy, their molecular alignment is broken, so you can't again polarize the dielectric. Okay. Now consider another problem. Consider a hydrogen atom with Bohr radius A is equal to 0.52 Armstrong is situated in between plates of a capacitor. So there is a hydrogen atom situated in between plates of a capacitor, and I have given them a 500 volt supply. So I have given them a 500 volt supply. So how far will their positive and negative centers will apart due to polarization? You know that if you kept a hydrogen atom, definitely this will get polarized, the negative sign towards positive and plus here. So we have to calculate what is the basic meaning. We have to calculate what is their dipole length. Since we know that the dipole moment P is equal to Q into D, and D is equal to N, where P has another expression, P is equal to alpha into E, and alpha is called the polarizability of the hydrogen atom. So this alpha can be found out. Now what is D? It's an easy problem that P is equal to alpha E divided by Q is equal to D. So you know about the electric field, but the separation is given as S, and from our expression E is equal to V by S. What is V? V is the potential applied, capital V. So you can easily find out as alpha into V by Q into S is equal to D. So getting the data of alpha, V, Q and S, you can find out how much these charges are separated. So on substituting the values for alpha, V, Q and S, we can find out the dipole length D is equal to 2.2 into 10 raised to minus 16 meter. So this much small distance the charges will separate. So in this session we have considered a sphere of radius r, which is a linear dielectric material placed in a uniform electric field E0, and we found out that the electric field inside the sphere En is equal to minus chi e by 3 whole raised to n by E0. And also we had derived what is the force on a dielectric slab kept in between plates of a capacitor. And at last, for a dielectric medium having high density, we have obtained this Clausis-Mossotti equation. And this Clausis-Mossotti equation is the connection between the susceptibility, polarizability and the dielectric constant. And you have obtained two equations connecting alpha and chi, E and K. So in the next session, we will discuss the idea of multipole expansion and some classical image problems. Thanks for watching my session, and meet you soon.